Do you remember the early days of 2020? I mean, the whole world was scrambling, and we were just flooded with charts and graphs, all trying to predict what would happen next with the pandemic. Some models said it'd be over in weeks, others said, years of lockdown. They were all over the place, and it just created this fog of confusion right when we needed clarity the most. And this quote right here, it really sums up the whole mess. It's from a famous model out of Singapore that got a ton of media attention for predicting when the pandemic would end in different countries. But then they had to retract it. They had to pull it all back. This statement just perfectly captured the problem. The predictions just weren't holding up to reality. So let's put on our detective hats for a bit. What was really going on behind the scenes that made these forecasts so unreliable? We're going to dig into the science, the data, and the surprisingly simple solution that finally brought some stability to all that chaos. Okay, so at the heart of almost all these predictions was one main tool. It's a model that has been the absolute bedrock of epidemiology for more than a century. Meet our prime suspect, the SIR model. Now, the SIR model is, at its core, a beautifully simple idea. It takes the entire population and just divides everyone into 3 big buckets to see how a disease is moving. First, you have the people who are susceptible. They can still get sick. Then you've got the people who become infected. And finally, the people who are removed, which means they've either recovered or tragically passed away. And the whole thing is like a one-way street. You start out as susceptible. If you catch the virus, you move over to the infected group. And once you're not infectious anymore, you enter the removed group. It's a really simple but powerful way to think about how an epidemic works. But here's the catch. To turn this simple concept into a tool that can actually predict the future, you have to feed it 2 absolutely crucial numbers. The first is beta, that's the infection rate, how fast the disease is spreading. The second is gamma, which is the recovery rate. If you can get these 2 numbers right, you can predict the curve. But if you get them wrong, well, that's exactly where the trouble started. So the whole thing hinged on how these numbers, beta and gamma, were being calculated. Because when researchers looked at the day-to-day data, they found something really, really unsettling. The numbers weren't just a little off, they were wildly unstable. You have to remember, in the early days of the pandemic, the data we had was limited and messy. Data scientists have a great word for this: noisy. It's like trying to tune into a radio station through a ton of static. And when you feed that kind of staticky data into a model that's trying to guess both beta and gamma at the same time, the model just freaks out. The numbers would swing wildly every single day. And I mean, just look at this. This shows the change in those key numbers in just 24 hours back in April 2020. In the UK, the infection rate, beta, barely budged. Pretty stable. The US, okay, not too bad either. But then, whoa, look at Russia, a 41% change in one day. And Turkey, the numbers are just jaw-dropping, a 174% change in beta. At that point, your model is basically useless for predicting tomorrow. This chart really puts it into perspective, doesn't it? On one side, you have the UK, with a change so small it's barely a blip. And on the other, Turkey, where the estimated infection rate just exploded overnight. And again, it's not like the virus itself changed that dramatically in 24 hours. It was the model that was struggling with the data it was getting. And a clear pattern started to emerge from all this. The models were the most fragile, the most unstable in developing countries. And why? Well, it most likely came down to challenges with consistent data collection and testing, which just made their data even noisier than elsewhere. The models were just buckling under all that uncertainty. So, if your model is broken, what do? Well, researchers realized they needed a way to get a stable, clear signal out of all that static. And this led to a pretty amazing breakthrough, a much, much simpler way of looking at the problem. Think about it like tuning an old analog radio. Trying to guess both beta and gamma at the same time was like trying to fiddle with 2 different tuning knobs at once to find a clear station. You're just going to get a lot of static, right? The challenge was to figure out a better way to find that one clear signal in all the noise. And the answer, funny enough, came from a philosophical principle that's been around for centuries: Occam's razor. You've probably heard of it. It basically just says that the simplest explanation is usually the best one. Don't make things more complicated than they have to be. So applying that principle led them to a new method they called single parameter estimation, or SPE. The old unstable method tried to guess both beta and gamma at the same time. The new SPE method did something way simpler. They decided to only solve for one of them. And the logic here is just, it's so intuitive when you hear it. The recovery rate, gamma, is mostly about biology, how long a person stays infectious. That shouldn't really change much from day to day. But the infection rate, beta, that's all about our behavior. Social distancing, lockdowns, masks, that does change, and quickly. So the researchers said, let's just take a stable, medically sound number for gamma, lock it in, and then use the daily data to solve for the one thing that's actually changing all the time, beta.
Okay, so that's the theory. And it sounds really good on paper, right? But the billion-dollar question is, does this simpler approach actually work in the real world? Well, they put it to the test.
And the results were kind of stunning. Remember that wild instability? With the old method, the average daily change in the infection rate was over 26%. With the new, simplified SPE method, it dropped all the way down to just 1.4%. They had found the clear signal in the static. But the most convincing proof, the real nail in the coffin, came from a real-world test case. They looked at Norway, a country with excellent data and really transparent reporting. This was going to be the ultimate validation. So using their new, simple SPE model, the researchers calculated the effective reproduction number, the famous R number that tells you how many people one sick person infects. For Norway, on April 6, 2020, the number their models spit out was 0.70. Now get this, in what has to be one of the craziest coincidences, on that exact same day, the Norwegian Minister of Health held a press conference. He announced the official government estimate for the R number, which was calculated by their top public health experts using all their complex tools. And their number? It was also 0.70. It was a perfect match. The simple model had produced the exact same result as the sophisticated official one. So, what does this whole data detective story tell us? What's the final verdict on how we should build models when we're in the middle of a crisis? The lesson is profound, and honestly, it goes way beyond just COVID modeling. When you're dealing with uncertain, incomplete, noisy data, adding more complexity to your model doesn't always help. In fact, it can make things much, much worse. Sometimes a simpler, more focused model is not only more stable, it's actually more accurate. And this leaves us with a pretty fascinating question to think about. I mean, we live in a world that is obsessed with big data, with complex AI and machine learning. But as the story of these COVID models shows, maybe, just maybe, the smartest answer isn't the most complicated one. Maybe the pursuit of simplicity is still the most powerful tool we've got.